Welcome to another GCBASIC tutorial video. This is part 14 for the 16F legacy chips. So a lot of what I'm doing here applies to the 10Fs and 12Fs, but they're legacy, and you can see my post up on Ko-fi if you want to understand what I mean by legacy. So this is part 14, pulse width modulation, many ways of doing it in GCBASIC. So please like and subscribe, tick it, that means give it a thumbs up, watch the video all the way through. Be very grateful. Thank you. So using pulse width modulation, many ways to dim the LEDs. Well, as you're going to find out, never perfect. This is why legacy chips have a little bit of an issue with pulse width modulation. So I'm assuming you've done all the prerequisites. You have the GCBASIC software installed, GC Studio, you've installed your programmer, you can program that attached PIC. You have some LEDs, a pot, some switches, a USB TTL, and an LCD. If you haven't seen the one on USB TTL, go watch that tutorial because we're going to be using the serial connection. This is the board I'm using. It's actually a PIC-dem2 board, demonstration board. And what we've got, I'll just draw what we're going to be using. Pointer options, pin. We're going to be using number 9, which is the 4 LEDs. Or can we? I don't think we can. I'll do some stuff on that LED, on the LEDs, but I can't do an awful lot. I'll explain why. But we're going to be using a particular port on the chip, and we're going to expose it through this thing called the pigtail, which is this rail on item 15. We're going to take one of the connections on here and study it and see what the impact is. Now, normally at this point, I show you my board. Maybe I should show you the board, yeah? Let me just take you to my desktop. I'll go out to my desktop if I can somewhere else so you can't see it. Desktop. Oh, I think I deleted the picture. I had a picture in there. No, I didn't, did I? Oh, here we are. Here's a picture. This is what my board looks like. A bit of it, we're looking across it. We've got some LEDs here on the left, LCD, big chip sit down the middle, but we've got this thing called the pigtail connector, and I'm going to hook in the ground and a sensor so we can see the PWM signals, pulse width modulation signals. Because if I show you what's actually on the desk cam at the moment, normally this is always good fun. Look, I got cameras and cameras and cameras. Let me bring the light up. I've got an oscilloscope down here, bottom left. Don't worry, you don't have to see it. I've got the 4 LEDs at the top. I have another camera. That camera is this camera here. Like you can see my fingernail underneath it. That camera is that, because otherwise you wouldn't see anything. Here's the chip, and here's the pigtail connector. And currently, I'm hooked into RB3. And what we're going to see on my PC is some results. So I've actually got it hooked up at the moment to RB3, but shortly I'll have to go to CCP1 because that's what we're going to be using. That is where the pulse width modulation signal comes on these boards. You can't change it. It's fixed on that port. Go to the data sheet and check it out. That on some chips, you can move it to one other alternate. Let's go do that. So let's go there and figure out whether I'm telling the truth or not. Here's the program we will be using, Control B. I am going to go out to PIC info, PIC info. I'm going to pick my microcontroller from the list. Here it is. I'll zoom in on that so you can see it for a second. And I'm just going to go data sheet. In the background, when I click on it, because I wasn't clicking on it, it will go out and open up the data sheet. it's now opened up the datasheet. Here it is, full screen. And I'm just going to cursor down to show you. And this is the dilemmas of using the old legacy chips. You are constrained on, certainly on CCP, which is, I'll find it in a minute. Let me find a diagram of the chip. Gosh, it's hard, isn't it? Gosh, it's hard. Here it is, look. There's the chip. I'll zoom in on that for you. We're looking in this massive stuff for CCP1. And it's here on RC2. And there is no, this one is movable, look. You can change the CCP2, sorry, to an alternative. And I think you can change it to RB3 up the top here. So you can move things around, but very limited. If it was PPS, a more modern chip, we could put it on any of the outputs that we required, or a number of outputs. I don't want to oversell its capabilities. So I'm going to move my scope later on to RC2 because that's the CCP1 I want to use. Back to my slides. Hence, I've got two things sort of highlighted there. So let's have a look at what we're going to be doing. We are going to be turning an LED on and off. We're going to use something called a duty cycle, which is how much time it is on, and we're going to be using something called a frequency, and that's the width. And so I can't draw on that picture because it's moving, but essentially that's what we're going to do. We're going to vary the signal. And so pulse width modulation is just a set of pulses being sent out, and you reduce the average power of the electrical signal to the target device by chopping it into small parts. So the average of the volts and the current to be fed to the target, the load, is controlled by turning it off at a very fast rate. Now, some have fixed frequencies where you must, the period is fixed, and the higher the power, and the longer the signal is on, the higher the total power supplied to the load. And as you can see, the diagram shows, as you have it less, that's full on, you get full power, and then full off. So we're going to look at different ways of doing things. We've got ways of toggling, sort of making these 6 square waves, they're called. We can do that many different ways, and we're going to look at that using many of the different commands within GCBASIC. But we're going to see those on an oscilloscope to make it look easy. The oscilloscope that you saw on Descam was this little one from Gabtronics. Bought it a long time ago, Mega Mini Lab. It's very good. It takes 2 signals. It's a great little chip, a great little device. Recommend it to anybody, honestly. And we're going to see that operating. Why? Is because I've got some software. And I've got some software on my desktop, and we'll see signals on here rather than have to look at the camera. So what we're going to look at is at least 6 different ways, and we'll walk through the examples, okay? Now, I don't think that the legacy chips have 16 way. I don't think that's valid in reality, okay? But the simple way is just to turn a port on and off, number 1. You just turn it on and off, and we'll have a look at that. It's very simple. And then there is a method that is called PulseOut, and you can pulse out on a particular port, and it's quite useful if you just want to send a pulse out, like something to enable a signal for one pulse. Just use PulseOut, boom, with a time limit, boom, job done. There's another way called PWMOut, and you can send out a number of pulses. So if you have a stepper motor, you need to send 4 pulses to. PWMOut may be better than any other method because you can control the number of pulses. Then there is the CCP, which I've spoken about. Was it compare? Oh, I can't remember. We should look in there. We should look in the data sheet, shouldn't we, really? I can't remember what CCP stands for. If I type in compare, there you go. To capture and compare PWM modules. Well, we have a mode that's called fixed mode, and we have another one called variable mode at number 4 and number 5. And then number 7, we could create a similar signal using a timer. And the differences is that in some of these, you may need PPS. I don't think that's true. I'm going to revise this slide live, discard that. No PPS is required on any of these because it just doesn't have it. This is a better view of look at it. Is that on the first one, you can have that on any port. That's an output quite clearly. PulseOut and PWMOut, any port. CCP, they have to be on the particular port specified in the data sheet. And I'm going to delete this row as well because that's only right thing to do. There we go. The interrupt timer way, we're going to use a timer on any port. So we're going to see different methods. Let's walk the examples. Let's open up GC code, do it slowly. GC Studio, open it up. And then I'm going to open up my demonstrations, microchip PIC14 plus board 2010, and it will open the folder for me. I'll close down all the previous code we were using. Fantastic. Now, Control B to open up the demonstrations. Put your filter on if you want to get rid of all this stuff. So Control F, GCB, and turn the filter on. Now I'm just looking in here. Let's have a look at the first one. 241. Use pin IO to control the brightness. Okay, I am not even going to discuss the header. Look, it's there. It's the same. Nothing's changed. Or has it? Oh, nothing's changed. It's the same. So basically what I'm going to do is I'm going to toggle an LED. LED 3, if you remember, that is set to one of the LEDs on the board. Program that. I'm going to go out to desk cam, and we can see on the bottom right hand camera, let me just turn the light down. There we go. And the LED has come on, RB3. And that is LED 3 in our source code, by the way. If you look in our source code, Control B to get rid of that window. LED 3 is on port B, but it doesn't seem to be doing anything because we can't see it with our eyes. So why don't I bring up Gabtronics X? Look at that, fantastic! Look. We have an oscilloscope. I'll change the size of it. Look at that. We have an oscilloscope. Ooh, that wasn't right. We have an oscilloscope. I'll just bring it across. We have a signal. Look at that. It's fantastic, actually. Got to give the guy credit. I love this little scope. I'm trying to get that so that you can see it at the same time. So we got a scope. We can see signals. And all I'm doing is turning the LED on with a small delay of 11 microseconds, and I get a pseudo square wave. But I can't do anything else whilst that is running. So yeah, you can generate square waves by doing this, by matching it up. I think I needed 11 milliseconds, microseconds, or nanoseconds, sorry, and then 3 no-ops, and it sort of makes a square wave. It's a method. I wanted to show it. 242. Use PulseOut. Use PulseOut to control an LED brightness. Same header. So look at the. I'm now saying same do loop. PulseOut. PulseOut LED LED D3, which is the same LED as we chose before, for 12 microseconds, 12 microseconds. Is it microseconds? Must be. Getting tired now. Yeah, microseconds. There you go. And then do it all again. So if I press function key F5 and I program it, let me bring in the oscilloscope. Where's my oscilloscope go? There it is there. Looks like no difference because I was trying to emulate that. But you can see I haven't got any no ops or anything like that. And so if I change this to 20, 20, reprogram it, I can change the period, but not the duty cycles. The duty is how often, how much it's on during the cycle. You can see it's changed. So if I wanted to change the duty on that, I'll put it back to 12, and I'll put that to 3. It will give us a 25% duty cycle on whatever frequency that is, but it's 25% of the period. There we go. Now the oscilloscope isn't capturing it. This is quite fast, this program. If I ran it a lot slower, and this is the frequency here is fixed against the frequency of the chip. So if I go to the top of this program and change this to of 1 megahertz, 1 kilohertz, 1 kilohertz, will it make a difference down here? No, it did. Why is that made a difference? Let me just look at why. Oh, because the timing is different. Yes, the timing is different because I've got 12 here. Let me just put that back to whatever the 32 the default is. And then we'll reprogram that down and we should get our square wave back. Just reprogramming it. Back to our square wave. Great. Open up the next. PWMOut. So this is a function of the compiler. Compiler does all the heavy grunting for you. And essentially what this is going to do, you set up a couple of constants. You say, right, where is the PWMOut 1? And you can have up to 4 of them. I want that on LED 3. You can have an optional constant, optional delay after it's given the pulse, and you tell it to be an output. It's not required, but it's good practice. What I'm saying here is that give me a pulse. Give me a pulse. If we look in the syntax, function key F1 by highlighting it. So this is the channel we've selected, the duty cycle, and it's 127. So that's of 255, which is exactly 1/2. So that's 50% duty cycle. And how many cycles? How many? So you can actually control this. So we're going to send out 4 pulses and then stop. Let's have a look in our oscilloscope then, shall we? If this works, we should see 4 pulses and it will stop. I might have to change the scale here. Look, completely different frequency. Oh, I need to put a delay in it because it looks like it's continuous, look. But if I put a wait in here of 3 milliseconds, we'll see the pulses. What we're seeing here is the pulses are just continuous because of the do loop. I'll put a delay in it. We should see the pulses now. There we go. The oscilloscope is showing us we get 4 pulses, so we can arbitrarily send out 4 pulses at any duty rate. I picked 127, which is 50% of 255. That's the unit of measure there. So if I change this to 2, I just happened to pick an arbitrary value of 4 for this video. I will revert it back to 2 just for the and now we're getting 2. Brilliant. So we've already seen a whole series of ways of outputting these types of signals. 244, use fixed mode pulse width modulation via CCP. This sounds really complicated. Well, it's not. Same header. The CCP1 port on this chip, as we saw in the data sheet, is on port C.2. Set it to an output. Two very simple constants do everything. The PWM frequency, PWM duty. And then you turn it on with the command PWM on. You can turn it off as well, so obviously do that if you want to. There's some debug in here if you want to go and have a look at some debug, but we're focusing here on the basics. Watch this. Back out to my oscilloscope, and we will get nothing because my oscilloscope is on B3, not C.2. So I'm just going to stop, and I'm going to turn the light on, and I'm going to take my little wire out of here, and I'm going to put it in RC2, which I believe is there. Wow. And it's hard for you to believe that that looks like a square wave, but I assure you that is a square wave. It's just that the software I'm using is working. Now I could actually hook up a oscilloscope, and it will be 38. Now, what is important here is there is very little code inside of the program. The program consists of one command, a couple of constants, and set the port to an output. The rest of it is done automatically within a set of what are called scripts, and it then automatically sets up CCP1. Does it all for you. There is very little to do. It's called fixed mode because those two constants can't be changed. You can change the frequency. If I said I wanted to put this to 25, you can change the constants at this point. You can also change the registers it has set for you, but you'd have to learn what those registers are. As you can see, it's gone to a duty of 25. So let's assume for a minute you really wanted to have a greater level of flexibility. That's where the final program comes in this demonstration suite. Use PWM via CCP and an ADC to control the LED brightness. CCP1 is what we're going to be using. We'll have a look at it. Set the port as an output by defining a constant, and here's the command. Hardware, that's the H, PWM, channel 1, that's CCP1, 38, that's the frequency, 127, and that's a unit of 255, so that's 50%. And then down here, I can do some clever stuff. I can read the ADC in, which is a value of 250 to 255. I can send it to the same command, and we will get a varying signal. Down below, there's some optimization code. You can look at it in your own time. But if we look at this, there's no action on the second camera, but there will be, because I'm going to bring in my screwdriver. You can see the signal. You can see my hand coming on the LED. And as I rotate the potentiometer, that drops to 0 or to full. So now my potentiometer is controlling my duty. And you can also change the frequency on the fly. So this is variable mode, and all the grunt work, all the low-level assembly is all calculated for you. That's pretty good in reality. That's many different ways of generating a square signal. And if I put on my fancy, very fancy oscilloscope, you would get a square wave on that. And I'm sure that if I adjusted this, I wonder if I reset it, I'd get a better signal. Maybe I should have done that to start with. I'm just looking at the options here. Restore settings. Good. Oscilloscope's got 2 channels on it, look. Auto. Oh, look, I should have done that to start with, look. Trace, turn the trace off. Turn up the gain on. Oh, it's not much better, is it really? Probably the cable I've got, the way I've got it set up here. It's picking up some noise, etc. I've also got an LED I can see stick on there. Has that just changed it? I'd imagine it has. No, that's just me being dim. Put that back as it was. I'm just putting my oscilloscope back as it was. There we go. Yeah, it's just the shape of the signal is not too good, but that's probably my end. So what I wanted to show you is that you can generate signals in many, many different ways. Minimize that. And we've looked at 5 different methods here. That was from just pulsing the LED using PulseOut, which is actually on a port for a number of a time unit. We looked at Pulse PWMOut, where you can send up to 4 channels, independent channels, a duty cycle, and a number of pulses. Very useful for stepper motors. We looked at fixed mode, a couple of constants, and PWM on. And we looked at a variable mode where you just use a command, you send it the channel, and there's however many channels, up to 5, I think. There might be more than that. The frequency, and then the duty cycle. These are all 8-bit, and they all work. I think we're going to come back to the last option that was discussed here, which is number 6 later on. We're going to look at that. Let me have a look at demonstrations using an interrupt. Let me just check my slides. No, that's definitely the next video, because look, we've just done number 14 using PWM many ways to dim the LEDs, but they're actually generating square signals. The next one will be using an external interrupt to control an LED, so we're getting more and more advanced. And with that, enjoy.